Okay, good morning everybody. Still the attendance is very low. Okay, let's start it. Can you see my screen? And can you hear me? Okay, thank you. Let's start it. If any time you don't hear me or there is some interruption, you just tell me, raise your voice and tell me that you cannot hear me or cannot see my screen. Then I will do something. Okay, so let's go to the frequency response of a second order system. What we were reading. So there I discussed that if you have any system and it may be second order or first order, if you give some sinusoids, the output will be sinusoids, only the amplitude and the phase will be different, and the amplitude and the phase will change for each and every omega, whatever input you give. So it will be easier if you know the omega versus gain and omega versus phase plot. So easily you can calculate, you know that how much input you are giving, what is its omega, and then quickly from the table or from the graph you can see that the output phase and output amplitude, and then quickly you can calculate what will be the output. So this is for a single sinusoid. Now suppose you are giving some input which is not at all sinusoid, but you know from the from the Fourier series that each signal can be transformed into the sum of many sinusoids. So the input signal you can convert into sum of many sinusoids, and for each sinusoid you can calculate what will be the output, and for each output and for overall output you can add them using superposition theorem and you will get overall output. That is the way you can calculate the output using frequency response for any arbitrary input. Now, as I said that our problem is different. So we know the output, we need to know the input. So whenever you get some output response, you can grab it, you can convert it into a sum of sinusoids. So if you are in continuous domain, which is not very usual, you can do it by Fourier transform, or if you are in a discrete domain, you have to grab it using data acquisition box, and from that data you can use the first Fourier transform so that you know the different sinusoids and their frequencies. So if you know the different sinusoids and their frequency, by reversing it, you can calculate the input sinusoids and input frequency, and you can sum them all to know what the input is. So from the output, you can calculate the input or the measured quantity. So that is the main idea. And last class I discussed that for a second order system, if we plot both the linear scale omega versus gain, not in the log scale, you will get this type of plots. And if you plot that omega versus phase, you will get this type of plots. And I said generally that under-damped system is most preferred because although it is oscillatory, it reaches the steady state early and oscillation is better. Otherwise, you have to wait. You don't know how it will reach for the over-damped system and the settling time is more. Now, from here I discussed that zeta what you need to take. So if you are a system designer or the measurement system designer, so zeta is preferably 0.6 to 0.7 we generally take, because for such zeta you will see that the phase angle is changing from 0 to 180 fine, but there is no drastic change. You see that it's almost linear change. From 0 it will keep on increasing as the negative values, and then infinity it will go to minus 180. But if you take zeta very small, you see that sharp change near the corner frequency, which is omega by omega n equals to 1. So this much we discussed in our last class. Now there is some problem with these two figures. The first problem is here nothing is in log scale. So, but you know, if you want to calculate or if you want to transform any arbitrary signal into its Fourier series, you will see it consists of the many sinusoids. Among them, many of sinusoids whose frequency is very high, and there will be many sinusoids whose frequency is very low. So you need to convert it. For example, you are using an amplifier circuit and you are giving some input. Say you are singing and you want this to amplify. Then you will see that your voice or the input consists of many sinusoids, which is ranging from very low frequency to very large frequency. Now, if you want a chart which will consider very low frequency to very high frequency, you will see your chart, if it is linear, it will keep on increasing on x-axis, and it will not be inside a graph. You need to add 4 or 5 graphs and it will be a very long graph. That is not very usual to do, because suppose if you are doing 0.1 radian per second to 10 to the power 6 radian per second, so you need 0.1 to 10 to the power 6, that means 10 to the power 7 number of lines. It is very inconvenient. So to do so, generally what we do, x-axis curves, x-axis is taken in the logarithmic scale. Okay, so x-axis is not linear scale. For both the amplitude and the phase plot, x-axis will be in logarithmic scale. Now for y-axis there are two curves, one is phi and another is gain. So for phi or phase angle curve, y-axis will be linear scale, because phase angle generally can vary from 0 to minus 360 or something like that, or even more, but it is not very high. So it is taken in the linear scale. Now for the gain plot, what will be the y-axis? Y-axis will be in so y-axis will be in decibel. So in how we will do it, generally you have seen that here y-axis we have taken as the ratio of the output by input, but the y-axis is generally taken 20 log 10 output by input. Okay, so we call it as a dB. This is customary. We take it in dB. So y-axis is linear scale, but the unit is dB, which is 20 log 10 ratio of the output by input. So here in Viva, student used to do mistake. We used to ask that what will be in x-axis for a gain plot. They said it is in a log scale. No, it is not in a log scale. It is in a linear scale. Although the quantity we plot, it is in dB. That means 20 log 10 output by input. So that is the case. So it is never in the log scale. It is a linear scale, but we plot the unit of dB. That means 20 log output by input amplitude, log 10 base. So now you see that. So we usually do semi-log graph paper. Semi-log graph paper means y-axis, x-axis will be, one axis will be in log and another axis will be in linear scale. So it is called the semi-log graph paper. So in semi-log graph paper, x-axis we plot the omega or the frequency, and the y-axis what we plot, it is generally the for gain plot, it is in dB, 20 log 10 output by input amplitude, and for phase plot it's in degree. Okay, now there are two ways we will be discussing. First thing is that if we know a, okay, let me see if any query you ask or not. Anybody want to ask anything? Okay, no question. Then I proceed. So now there are two things. One thing is that suppose you know the system transfer function and you want to know the plot. So whenever we plot such, one thing I forget to tell, whenever we plot such, that means one is in x-axis is in log scale and y-axis in dB and in linear scale, and y-axis is in angle which is also in linear scale. We call this plot as a semi-log plot because one axis in log, and this plot, the semi-log plot, is known as the Bode plot, very popularly known as the Bode plot. So there may be two things. One thing is that if you know a transfer function of your instrument, you can plot the frequency response, which is called Bode plot of the instrument, and you know from there you could know that if you get some output, what will be the corresponding input. So this is very uh, usual and easy to follow, that if you know, if you have built an instrument, most probably you will know the transfer function of the instrument, and from there you can plot the Bode. That means phase versus frequency versus gain and frequency versus phase. Now the thing is that how you can plot such thing. So now you imagine your x-axis is log omega in log and y-axis is 20 log 10 base amplitude, output amplitude by input amplitude. Now if you know a transfer function of the instrument, how you can plot, how you can draw the Bode plot? That is one question. And the next question is, sometimes we need to work in such an environment that we don't know the transfer function of the instrument. So in such a cases, you have to do some experiment and determine the transfer function of the instrument. And then once you determine the transfer function of the instrument, you can use that transfer function as well as the Bode plot from Bode plot to know the input from observing the output. So this is the two approach. Both of the things we will discuss here. In fact, in our control lab, control and instrumentation lab, we have an experiment where you need to determine, we generally give you a black box which has inside some circuit. You cannot see that, only you can see is the input terminal and the output terminals, and from there you need to determine what will be the transfer function of such box or transfer function of the system inside the box. So to start with, you need to know how you can plot a Bode, how you can draw a Bode plot. There are two approaches. First approach is very simple. So you take the transfer function and you make a column, x column and y column. In x column, you keep on putting the different frequencies in radian per second. For example, you can start with 0.001 and then gradually you can go to 10 to the power 6. So you write many frequencies in the column X or column omega. In another column, which is the gain column, you calculate. So if you have a transfer function like this, now let's see equation 3.215. If you have this here, you know the k values because you know the system, you know the omega n because you know the system, you know the zeta because you know the system. So if you know such, now you think about omega, which is in you are considering, you wrote many omegas in the x-axis in the first column, x column. So there you wrote many omega. So for example, if your omega is 0.1 or 0.01, you can substitute that omega value in the equation 3.215 and you can calculate the gain from the next equation, which is 1 by root over 1 minus omega by omega n square whole square plus 4 zeta square omega square by omega n square. Here the value of zeta you know, here the value of omega you know, value of omega is 0.01, you put it, omega n you know, and from there you will get some value and then you do 20 log of that. Okay, 20 log of that. So, and then the value you will get, which is in dB, you write that value in the corresponding row of omega equals to 0.1. Then similarly, you calculate the gain in dB for the different values of omega. And then you plot these two columns in your semi-log graph paper. You will get the amplitude plot. And similarly, on the third column, you can calculate the phase, which is tan inverse 1 2 zeta by omega n minus omega n by omega. So here you know the value of omega n, value of zeta, and then you substitute the different value of omega, you will get the different phase, and you plot the omega in semi-log versus phase. So this with from the three columns you can plot them in two plots and then you will get the coding. So this is the first method, right? Any query about the first method? Let me see. If anybody want to ask anything, please don't hesitate. Students generally get little confused in the frequency response. Okay, Utkarsh is asking something. So in the Bode plot, if zeta is greater than 0.707, no response is observed. No, it is not such. No. Why response will be there? Let's go to the, you are asking zeta equals to 0.707. Okay, let's go there. See the zeta equals to 0.707. So may I ask which plot you mentioned, gain or frequency, phase? Utkarsh, can you write or say? Oh, no resonance is observed. Okay, fine. No resonance is observed. Okay, you may think about it is a resonance. So if it is okay, so you mean to say that if zeta is less than 0.7, you will not get any peak. That is the thing you are asking, right? Now I got your question. So if you are saying that if zeta is less than, if zeta is greater than zeta is greater than 0.7, there will be no peak. This is almost flat, right? So from the frequency response, maybe you are asking. So if you draw this omega versus omega n and gain from the different values of zeta, certainly if you will see that for the zeta which is less than 0.7 or 0.8, you will not get the peak. That is certain thing. This is a very good question. So if you can draw the pole zero, now you are learning the control system little bit. So if you can draw the pole zero plots, from there I can explain, or other way also I can explain. Let me see if I have this curve or not. So yes. So if you see that if your zeta is more than zero point 0.7, what will happen basically, if you plot the poles and zeros, you will see that if your zeta is zero point 0.7 more than zero point 0.7 or so, you will get some complex conjugate poles. And when the zeta will increase, that the complex part will little bit coming close, and gradually it will come to a single point and then will go away. So if you see, if there is uh, poles which is a complex conjugate, so you will get a double pole at the same point, which is omega by omega n equals to 1. And there, if you have the zeta less, you will see that you will get sharp peak over such, over uh, near the corner frequency. That means omega by omega n. That is what the reason, if you have a second order system or two poles at some point omega by omega n, so near the corner frequency you need to take few points so that you can capture the peak. But when zeta is greater than 1, when if you plot it, so there is as such only two poles, and from there you will get minus 40 dB decay such. And you can think about this from the physical perspective. So if zeta is increasing, that means you are increasing the damping. So in such a cases, you will not get such peak. You will get little bit damped. So if you have two poles which are not complex conjugate at the same point, what you will get? You will get little uh, damped response of amplitude. So if you think about the first order system, if you have a single pole, so if you try to plot, you will see that your plot comes and then minus 20 dB per decade is goes down, and near the corner frequency it is little bit damped. So if you have two poles at the corner frequencies, and poles are not complex conjugate, they are real poles, you will see that from the corner frequency we will get minus 40 dB per decade slope, and that is little bit lower than the asymptotic plots. But if you have complex conjugate poles, what you will see, that near the double pole or the corner frequency, you will get little bit rise of the gain plot. So that is the way it helps. Okay, is it fine, Utkarsh? So now if we come back to our discussion, so what we are discussing, we are discussing that how you can draw a phase plot and the gain plot if we know the transfer function. So first approach, what I said, you make three column. In first column you wrote many omegas, and in the next column you calculate the gain for those omegas, and in the next column you calculate the phase. So in the first plot you plot the omega versus gain, and in the next plot you plot the omega versus phase. Once you plot it, it will be your Bode plot. Now this is a very tedious and laborious way to plot. Although now you have the computers and different apps where you can directly give the transfer function and it will give a direct Bode plot. That is obvious. But still, if you want to draw it by hand, this is a laborious process. And it does not carry much physical significance also. So now let's see, there is another way of thinking if you can plot it by seeing the transfer function. not by calculating the gain for each frequency. How you can do it? You see, if you have a transfer function like g1, g2 or something, so transfer function may be combination of many poles and many zeros, and so each poles and each zeros you can consider it as a single transfer function. So if you can do the logarithmic in the both side, because we are doing the dB, so what will happen, the right hand side, the combination of all transfer function will go, and what will happen, it will be additive, not the multiplicative. So this is the beauty of taking log. Now if you see, now let's think about a transfer function which has a pole. What will happen if a transfer function has a pole? You have to first consider the frequency at which the pole happens. For example, now let's think if a transfer function is 1 by s plus 1. Where is the pole? Pole is at 1 radian per second. So after 1 radian per second, the gain plot will die down with a slope of minus 20 dB per decay. Per decay means in 10th. 10, one cycle of frequency, that means 10. And this will slope, it will go down, and before that it will be a straight line up to the corner frequency. So the asymptotic plot will be a straight line up to the corner frequency, then a slope at minus 20 dB per decade for a single pole. Now for a single zero, what will happen? Same way, it will be a straight line up to the corner frequency, and then it will go to plus 20 dB per decade slope, keep on continuing increasing in such way. So this is the way the if zero happens. Now this is a first order. Now if you have a two poles, which is a complex conjugate, if you don't have complex conjugate, you can consider two poles as a two first order systems and add them. If you have complex conjugate, what you will get? You have a corner frequency and at omega equals to omega n, and at that corner frequency, before that your curve will become straight, and then after that the curve will fall at minus 40 dB per decade. Why minus 40? For one pole it is minus 20, so as there are two poles it will be minus 40 dB per decade. If there are three poles it will be minus 60 dB per decade. So that way it will fall. So, and then if that's what Utkarsh said, that if zeta is less 0.6, 0.1, 0.2 such, so you have to take few points near the corner frequency so that you can capture the peak in the near the corner frequency. If zeta is not less than, if zeta is more than 0.8 or so, so then there is no need to do it. You can little bit damp it and you can plot that. You can plot exactly compared to the from the asymptotic plots. So now once you have a big transfer function, you can decompose them into a first a pole, series of poles, a series of zeros, even if a series of second order systems, and then you can plot individually considering the corner frequency, and then after plotting such you can add them together to get the final plot. So in this way you don't need to calculate the frequency versus gain at each point, rather you can do it by seeing the transfer function and then calculating the corner frequency and then plotting it from the corner frequency. So this is the way you can plot it by seeing. Similarly, for a transfer function having a zeros, it will be a plus 90 degrees. Having a pole, it will start from 0 and end at minus 90 degree. And for a second order system, you have seen it starts from 0 complex conjugate poles and it will go to minus 180 degree. So for individual poles and zeros, you can plot them with the phi, omega versus phi, and then you can add all the phi at particular omega to know the omega versus phi overall. So in this way, by seeing the transfer function, you can plot the Bode. You can draw the Bode plot very easily first thing, so what you have to do, you will learn this in control system very detailed. So what you have to do, you have to know the corner frequencies, and the next thing what you have to do, you have to draw the individual plots for each poles, each zeros, and each second order poles, and then you add them. Similarly, you need to do it for the phase, and then you add them, you will get the overall phase plot and overall gain plot. Okay, now tell me if you have any question up to this. Any query? Okay, now you can think reverse way. What is the reverse way? Suppose you have a system which you don't know what is the transfer function, but what you need to know, you don't know what is the transfer function, but what you need to know, you need to know the transfer function of it. How you can do it? So as I said that we had designed a experiment of such, we call it that black box identification. So what basically you have to do, you have to do the basic, you have to give some input and you have to observe the output. What input you have to give? So suppose depending on the system which can take the input, let us think about it is an electrical system which is easier to give. So you can give an input which is a sinusoidal electrical input. So a simple sine wave you can give a sine omega t, say 5 sine omega t or so, and then output you can observe. So output amplitude, how you can observe, if you give such input, so you can take one CRO, cathode ray oscilloscope. Most probably you have not used them, you use generally DSO. So digital oscilloscope, you can take digital oscilloscope and you can see that how much output you are getting. Output will also be a sinusoid. So how much output you are getting. So if you see the output, you can calculate the output amplitude. If you see the input, you can know the what is the input amplitude. So you make the ratio input by output amplitude for different frequencies and do the 20 log of such and plot this dB versus the input frequencies. So you take this for a series of input frequencies and you plot it over the semi-log graph paper. And then what you have to do for the different input frequencies, you have to calculate you have to observe, not calculate, you have to observe the phase. How you can observe the phase? So you make a Lissajous figure. Okay, so that you might read it at some point. So you superimpose input and output. There is an option in the oscilloscope. It says that there is a knob or switch. Basically, it says that make a Lissajous figure. Lissajous figure making is simple. The two signals you need to superimpose. So if you superimpose two signals, it will make a Lissajous figure. Lissajous figures will be kind of ellipse, and its axis will be with a different angle from the different angle in xy coordinate. So ellipse does not mean it's always a ellipse of axis in x and y. It may be another axis or maybe axis having some angle theta with a x-axis, whatever may be. So ellipse will be formulated, and from there you can calculate the theta axis angle with this, and that will be the phase angle. Okay, so from Lissajous figure, you know the phase angle, so you can plot the phase angle. So ultimately from the experiment, what do you get? You get the frequency versus the gain, you get the frequency versus phase. Now you take the plot of frequency versus gain. So from that plot, what you can see that the slope of the plot, okay, you plot it, you can see the slope of the plot. Suppose at some point of time, you see that the curve suddenly start falling at minus 20 dB per decade. It means that you have a corner frequency. So to know that, you just extend this slope of curve, and then you see that where it is crossing, where it is cutting it, and from there you can find out the corner frequency. So from the plot you need to find out the corner frequency and the slope. Definitely you need to know the slope. So if you know the corner frequency, you will know that from where the poles and zeros are. And if you know the slope, you can know how is there a single pole or a double pole or double zeros. And from the calculation of poles and zeros individually, you can write the transfer function, and then combining together or multiplying together, you will get the overall transfer function. Now let's come, is there any utility of the phase plot? We generally used to ask this question in different vivas and for exam. So most of the students says that no, there is no utility of the phase plot in system identification. The answer is wrong. There is a huge utility. Suppose you have a single pole, okay, and your corner the pole and pole might be having at plus or at minus. That means at the right half of S plane or left half of S plane. Now from the gain plot, you cannot know that whether it is a right hand pole, right half pole, or it is a left hand pole, because for each pole the corner frequency will be same and it will be minus 20 dB per decade. Now by seeing the phase, you can know that whether it is a how the pole is located. So, so phase plot is also important by to know that the sign of the corner frequency, whether it is a left half or the right half. So by seeing the gain plot and phase plot, you can calculate or you can determine the transfer function of the system. So suppose you have some unknown instrument with which you need to measure it, and most of the times the manuals in the manuals of the instrument you will not get the transfer function, but for that dynamic measurement you need the transfer function to know. So then what you need to do, you need to do a series of experiment by giving some known input sinusoids and observing the output sinusoids, gain and phase of it. And by doing so, if you plot the body, and from there if you can identify the corner frequency, you can identify the slope of the curve, you can calculate the transfer function. So sometimes calculation of transfer function is very difficult if you take the very long frequency range. And what we generally use to do, that we know that at what frequency range we need to operate, what will be the input and what will be the lowest and highest frequency of the input. Generally we know it before operation. So what we generally do, we generally plot the body in this frequency range and see the gain and phase plot, and from such gain and phase plot we can calculate the transfer function accurately, at least for that frequency range. That is most important. That frequency range is most important. And if you know the transfer function, then you see the observe the output, and then you know the transfer function, so you know the input, so you can determine the input measurement or measuring quantity from such measurement. Now tell me if you have any query. Very interesting and things I discussed today. It's very interesting and useful that I feel. So so it is a, how you can draw a Bode plot, which is most important, and that you will learn in detail in control class. So I discuss a general way, and the next thing what I discuss is that the system identification, how you can identify a measurement system transfer function by doing an experiment, and particularly that the operating frequency range is important, in what range you need to identify the transfer function, because if you take very huge range, then you will see that transfer function is coming complicated, which may not always necessary to do. So we generally identify the frequency range and we plot, we give the input sinusoids, we observe the output sinusoid, from there we plot the gain, and then we do it gain in dB, and then we calculate, we form a Lissajous figure from input output to know the phase if it is an electrical system. And from there what we can basically we can do from that, we can do, we can calculate the phase and we can plot the frequency versus phase. So from the gain plot we can determine the corner frequencies and the slope in which the plot is decaying or rising, and from there we have an idea where the corner frequencies are, so where the poles and zeros are, and then we can calculate the transfer function. Although positive poles or negative poles cannot be determined from the gain plot, we need phase plot to determine such. So from the gain plot we can write the transfer function, and from the phase plot we can validate them, and combining both the plots we can determine the transfer function. So once we know the transfer function, we observe the output. Once we observe the output, we decompose the output in the Fourier series. We know the various sinusoids or harmonics, and then from those harmonics we go to the transform it to the Bode plot, and we see what the inputs are, and in from the individual inputs we sum them all, and we know what the input, how the input is varying with time. So that is the way we generally use the measurement system when the system is time varying. Okay, now tell me any query. Okay, so now, so here we end the dynamic response of a system. So you might ask that why I consider till the second order system. Generally, up to the second order system is considered. If it is not second order system or higher order system, what we can do, we can know the Bode plot, we can know the input from seeing the output. Also, we can know the time response by applying the input to such transfer function and then doing Laplace inverse. So this is customary. So, but there is no as such concept of rise time or peak time or such for higher order systems. So we generally confine ourselves up to second order system, although there might be higher order system more than second order system, and then that can be customized as a second order plus first order, like that combination of all. But the traditional way of saying, like the what is the peak, what is the peak overshoot, what is the uh, peak time, all those things are generally make no sense if the system is beyond second order. Okay, so in reality, if it comes, we need to do it a generalized way by using the Laplace inverse to know the time response, or if you know the time response or know the free transfer function, then you convert them to know the input, like that way. But there is as such, we will not read anything. In fact, in any textbook, you will not see any system which is third order and in such general treatment of such. Okay. So this is the thing. So this chapter we are almost coming to an end. Only one thing is remaining, is error analysis. That's what I said, that error analysis is remaining in the beginning I said. So maybe next class we will complete the error analysis, and then after that we will go with the electrical measurement. For example, measurement of charge, voltage, current, like that. Okay. So, so up to this part, you can read the Doeblin. Doeblin is very well written, and I'm following Doeblin blindly. Maybe 250 pages or so we have followed from the beginning. And error analysis, you can read the Sahani also, and also this part also Sahani is also good. They have also numerical problems they have solved. So you can read Sahani also with parallel to Dublin and see the numerical analysis and numerical problems and multiple choice questions. So please read Sahani as well. And next class we'll go with the error analysis, and that will be reading from Sahani, uh, some part of Dublin. And after that we'll go to the measurement of electrical quantity, which is fully from Sahani, mainly from Sahani. So now onwards, you take the book Sahani. Earlier, whatever I teach, you can read them from Sahani also, because there also it is well discussed with numerical examples and so. And then coming things like the measurements of electrical quantity, that is also Sahani. So Sahani book you can download, PDF copies are available, and you can start reading and solving numericals from there and solving multiple choice from there. Okay. So now today we shall end here. So tomorrow we have class from 9 to 11. So we will continue. taking classes from 9 to 11. And that's all. If you have any query, you can ask now. You can write it. You can raise your voice. And if you don't have any query, now we can end here. Thank you all of you for coming to class and attending the class.